Hello, class. Hope you're having a good night tonight. I certainly am. Um, Here we are, kind of midtermish, I guess, in this course. We've just gotten past the first exam and we're embarking on chapter 5 of your text. And so I thought it was time, especially given the content of chapter 5, to do another calculus snippet. Okay, so um, calculus, differential calculus is not a requirement for this course. However, to do any meaningful problems in microecon, you need to know some very basics, some just very basic differential calculus. So my intent here, and certainly with that first video that I made a couple, 2 or 3 weeks ago, I hope you've watched that and reviewed it and so forth. But in that video was to give you an idea of what a derivative is and how to find a derivative for a polynomial function. And so when we talk, especially here in chapter 5, about marginal product and marginal revenue, and anytime you hear the word marginal in economics, that refers to a derivative. Okay, and so I showed you how to find a derivative of a polynomial function there, but we encounter another kind of function here in chapter 3 that I want to mention, or chapter 5, that you'll need to find the derivative for, or the marginal for. And so at any rate, we have a little increment of learning in store for us here tonight that builds on what we've done before. So I thought I would cover this with you just a little bit, and then work one of the homework problems, or one of the end of chapter problems here. Really, I think it's problem number 1, where they ask you to find the marginal product for a Cobb-Douglas function. So at any rate, most of this I think you can get on your own in the reading and so forth. Hopefully, I will say that as I've provided also some review videos from my principles of microeconomics, that kind of helps you bridge the gap and understand some of the theory in this course. But I understand again that the mathematics that we use sometimes may look a little daunting. I will say that writing myself a note here to make sure I mention one thing here. That your book kind of sequesters some of the calculus in these paragraphs called what's it called again? A calculus alternative or something like that. And so I would like for you to try to read those. But again, I'm keeping the requirement of knowledge of calculus at a minimum. But hopefully, if you follow what we do on these videos, you'll be in good shape. So first off, let's review what we talked about just a little bit, just a little review of what we did in the first calculus snippet here a couple of weeks ago. So I'm going to go to the dot cam. All right, let me just say here that we use for a function in general. Okay, so maybe just real simple here. If I say y is a function of x, so we're used to working with these things like 4x cubed minus 2x squared minus 7x plus 3. Okay, I showed you in the first video how to find dy dx. Okay, dy dx is called the derivative. It's another function. It's derived from this first function. That's why they call it a derivative. It's a function that tells you how to find the slope at any value of x of the original function. And remember how we did this. I hope you've reviewed that and so forth, and you can do that. Okay, you do this term by term, and you carry the coefficient along here, but you take the old exponent and bring it down front. So this would be 4 times, that means multiply, 4 times 3x to the second power. Remember, you bump this old exponent down by 1. Okay, and then minus, you go to the next term, minus 2, and then, well, you take the old exponent, bring it down front, 2x to the first power, right? And then, well, this has got like an invisible 1 there. If I write minus 7x, it's minus 7x to the first. So at any rate, this is going to be minus 7 times 1x to the 0 power. Okay, bump that 1 down by 1. Of course, x to the 0, any number to the 0 power is equal to 1. And here, I'm just going to slide it in here. This is x to the zeros is equal to 1. So when I put this term in here, I just put a 1 in there, but I'm putting it in here for a reason so we can understand again how you differentiate a constant. You understand it to be like multiplied by the 0th power of the variable itself. So this is times 3 times 0x to, if you want to go to the -1, you can. But at any rate, 0 times anything, that's going to go out, right? So that's a 0 there. Okay, let's just work from right to left here. This is a 0 because the 0 came down front. And any number to the 0 power is equal to 1. So this is equal to 1, and this is 1. So this is -7. Okay, and so and this is a -4x. And then this is 12x squared. Okay, so this is dy dx, or also called the derivative of y with respect to x, or y prime. Okay, so again, what do we wind up with here? Okay, you can take this off if you want. So it's really this expression right here. So you see, you take this down front. So it's 12x squared minus 4x and minus 7. Okay. So I can give you, if you want some exercises on this or some practice on this, I can provide this for you, but it would be very repetitious. You should just be able to, and you can probably go out on the internet and find out just basic derivatives. If you just Google that, exercises and basic derivatives, you'd find lots of examples of this, or at least derivatives of polynomials. So again, if I said a negative 7x to the third plus 4x to the, looky here, I'm going to give you a 1/2 power. Okay, that's okay. Plus 2 x to the 1/3 plus 4. So here, I mean, it's the same idea. You define y prime or dy dx, okay, either one of these, however you want to write it. You bring the old exponent down front and multiply by the coefficient. So this would be a -21 x squared, right? Bring this down front. So I shouldn't have to go through each of these steps here. It kind of gets a little messy, but this is -21 x squared plus 4 times 1/2. Well, that sounds like 2x to the 1/2 minus 1. You always bump this down by 1. So that'd be a -1/2, right? 1/2 minus 1 is -1/2. And then plus 2 times 1/3 is 2/3. Hopefully we know our math well enough to understand that. Times x to the 1/3 minus 1, or 1/3 minus 3/3 is -2/3. Okay. And then, of course, the derivative of a constant is 0. So it's the same idea here that we did above here in obtaining this derivative here. It's just that we have some fractional exponents, but it's the same idea. Okay. I will say that sometimes you'll see a derivative expressed this way, where they'll make a funny looking backward 6 here. Basically means dy dx. It's for multivariable functions, but you're going to see this in your book. I noticed, they give you this on page, oh gosh, I don't see it offhand. But yeah, here we go. On page 147 of your text, you'll see that basically dq/dl. Okay, it's just that you have taking the derivative of a multivariable function. So in other words, let me give you an example of that just to make sure we understand. Say if I had z here, okay, z is 3x squared plus 7 y to the 5th plus 8. Okay, then I can find the derivative of z with respect to x. Now, when you do that, everything else is a constant. So you're going to treat y like it's a constant. So like it's just a number. So the derivative of z with respect to x, we just recognizing that you got more than one variable on the right, okay? But you're going to hold one of these constant for the moment. So this is just 6x to the first power. If this were a number like 7 or like 10, 7 times 10 to the fifth, what have you, these would just be two constants that would go away in the derivative. Okay, so the idea here is this is your variable you're differentiating with respect to. You could also find the derivative of z with respect to y. They actually call this the partial derivative of z with respect to y. But the idea here is we go back to the original function and you treat now x as a constant, okay? And you're going to treat this as your variable. So the derivative of a constant is always zero. So the derivative of the first and the last term would be zero. And so this would be 7 times 5y to the fourth, which would be 35y to the fourth. Okay, so that's all that is. So when your book gives you this notation, as they do on page 147, okay, the idea is they've taken some output function that's a function of both k and l, and they found these partial derivatives. So when you find the derivative or partial derivative of q with respect to l, q is a function of k and l. They're treating k as a constant here, and l is your variable. And here they're treating l as your constant and k as your variable. So let's just look at this a second here in this calculus alternative here. We could put some values in here if we wanted to. Here, they're looking at an output function, okay? So first off, let me make sure we understand what an output function is. There's different output functions. The simplest output function is one of this form right here, okay? Now, when we talk about an output function, okay, so I'm going to write that where we can see it. They say Q equals AK plus BL. AK plus BL. The idea is that the quantity of output, this is output, okay? Chairs, maybe, or tables, whatever it is. There's a formula that'll tell you how much output you can produce over time. It depends on how much capital. This might be machines, but at any rate, it's the old way of spelling capital. So, but this is capital. And so this may be machines or floor space or something like that. And this is labor. So this would be workers and so forth. So you have to have workers and capital working together to produce output. A and B are just constants here. These parameters or constants will kind of give you the formula of how to combine units of capital and units of labor to get units of output. So for instance, Q output could be seven machines plus 14 workers. Okay, now think about this a second. This might be the environment you would have if you're producing tables and you kind of need 2 workers for each machine or something like that. Okay, so if you have one machine, you need 2 workers and so forth. But there seems to be some fixed proportions here, and your book talks about that a little bit. But the point I want to make here is this is giving you output in terms of machines that you're using, in terms of labor or workers that you're using in a period of time. So if you were to combine 10 machines, 7 times 10, plus 14 workers, so it just doesn't matter. We could say 12 here. Okay, you could get your output here by saying that this is 70 plus 14 times 12. What's that? 14 times 12. I should know that, but I can't think of that for the moment. I guess that's 168. And so 168 plus 70 is, I know, 238. A guy who has a master's degree in math should be able to do that in his head, but sometimes it's not easy. So at any rate, 238 tables or whatever it is. So at any rate, we are combining labor and capital together to get output. Okay, that's all this formula here means for various values of A and B. At any rate, your book will have you find things like the average product of labor, where you'll just take Q over L. If you find the average of anything, you take the total output and divide by the number of workers. So this would be the average output per worker. So in this case, for instance, this would be 238 tables, okay, divided by the number of workers here. It looks like it's 12, okay? So if you took 238 and you divide by 238 and divide by 12, you get the average output per worker. So this is 19.83 tables per worker, okay? 19 tables per worker. So that's kind of telling you what the average output per worker is. And you can find the average product of capital as well, where you get tables per machine and so forth. But at any rate, they also have you find marginal product of labor and capital. Let's look at marginal product. Now, your book says that by definition, the marginal product is the change in the output, okay, divided by the change in the labor input. Likewise, marginal product of capital would be this, but divided by delta K. Maybe we'll do that in a minute. But what this is always is the derivative. Okay, this is the derivative of this variable with respect to this. It's dq/dl, or we can write it this way, given that, okay, it's the derivative of q with respect to L. We come back up here and we're going to differentiate this with respect to L. Okay, so you have a function here, output function. It's a function of two types of inputs, capital and labor. So if you're going to find the derivative of Q with respect to L, you're going to treat K, capital, as a constant. You're going to hold constant the number of machines constant for a little bit. Okay, and you're going to see how output changes with labor. That's what a marginal is. Okay, a marginal product is telling you, is a short run measure. It's telling you that in the short run, you're fixed, your level of capital is typically fixed, and you want to see how output changes with labor. So you take the derivative of Q with respect to L. Okay, that's telling you how Q changes with L. And so what is the derivative of this with respect to L? Well, you treat this as a constant and you just pull this coefficient down. So this would be 14 times 1 L to the 0. Of course, L to the 0 is 1. So this is just equal to 14. I mean, if you want to write it that way, you can. L to the 0, knock the old exponent down by 1. But any number to the 0 power is equal to 1. So this is just 14. Okay, the marginal product of labor here for this output function, let me back this off, is simply 14. What do you think the marginal product of capital is? This is how, it's telling you how output changes with capital. So what are you going to hold constant now? You're going to hold labor constant. So maybe you can't hire and fire any workers, but you can buy or rent additional machines or get rid of machines. So now you want to see how your output changes with changing the level of machinery. You see, these are measures that apply in what's called the short run. These are short run measures. In the short run, economists define the short run this way. They define the short run as the length of time in which one of your inputs is fixed. It might be labor, it might be capital. Typically, it's capital. Labor is usually more liquid or easier to change in a period of time than it's capital. You know, if capital is machinery out on the floor, it takes a while to get a new machine in the factory, or double your floor space or something like that to accommodate more machines and what have you. Workers, you can generally hire and fire more on a daily basis than you can acquire machinery. But there may be instances where capital is more liquid than labor. But so at any rate, in the short run, one of these is fixed. And I will say that, you know, usually labor is the more liquid input. And so managers typically will make day-to-day decisions affecting the level of labor in the plant or used in the plant. They may have someone work overtime or something, tell someone to take the day off or something, but they generally don't go acquire a new big machine to put out on the production floor, you know, simply to satisfy another small contract or something like that. So the point here is those short run decisions pertain to these marginal products that we're finding here which assume that, just by definition in the short run in economics, we assume that one of your inputs is constant. So in this case, when we find the marginal product of capital, we're assuming here that labor is your constant, and this is your variable now. So if you go back up here, this would drop out when you take the derivative. It's a constant, it's just a number. So the marginal product of capital is 7. Okay, so this is the derivative of output with respect to capital. So this symbol here, it kind of replaces the delta here. It tells you how output changes with capital. Or if you want to write dq, dk, that's okay. You just understand that quantity here is not a function of a single variable like we had with our polynomials. Only it's got a function of 2 inputs over here. But you're going to treat one of these as a constant. So this is a constant here. So this is just 7, right? That's why your book gives you these formulas here. The marginal product of capital is equal to A. Marginal product of labor is equal to B, where A and B are the coefficients here in your production function. So I hope that once you grab onto that, this discussion here makes sense to you. When they find these marginal products, that should be straightforward to you. Okay, it's nothing esoteric. We may look at problem 1 here in a minute just to make sure you've got this, at least part of the problem. Now, they introduce, though, for you here a new production function. It's not a simple polynomial like you have here with 7k plus 14l, say. They introduce what's called a Cobb-Douglas production function. And there's a lot about a Cobb-Douglas production function that's very, very real world, but it's kind of beyond the scope of our class to explain why a production function like this is real world. But I will tell you that it really is. But it's not a simple polynomial. You notice you're combining capital and labor together, but instead of adding terms involving capital and labor, you're multiplying them. Okay, so here is a Cobb-Douglas, a general Cobb-Douglas, where output is capital raised to some power. Whoops, I'm used to using Greek letters here, and they don't use that in this book, so never mind. Q is equal to KA plus times L to the B power. Okay? All right, so an example of this would be Q is equal to K to the, let's just say 1/3 L to the 2/3. Usually, and I'll pick this out for a reason, usually these two exponents here add to 1. When they add to 1, they have special properties. They don't have to, okay? This could be K squared L cubed, but I'm just saying that when these exponents add to 1, then it becomes even more real world, very much more real world. And you see this out there in industry and so forth, lots of places. Okay, and before the course is over, I may be able to give you a little more explanation of this. But we can work with this. Okay, notice here they find the marginal products of labor and capital here for this production function, just like they did up here by finding the partial derivatives or the derivatives of Q with respect to K and L respectively. So for instance, the marginal product of labor would be the derivative of Q with respect to labor. Okay, so you'd have to differentiate this thing with respect to labor, or you can say it's the partial derivative of Q with respect to labor. Okay, so how would you do that? Now, we're not adding these together like we did here. It was real simple just a moment ago when you had a function of this form, okay, which is what we had, which I threw the paper away already, but I don't know what did I do with that. Here we go. It was real easy to say that here when I was finding the marginal product of labor, I was going to treat this first term here as a constant and just throw it away. Now I'm multiplying powers of K and L together. So it's the same idea, but this could be a little confusing to you. Okay, so you're going to treat now this as a constant. I'll just circle that lightly. You're going to treat that as a constant. So you just bring it along, okay? just as you would if this were 4L to the 2/3, the derivative would be 4, then times the derivative of this. Okay, so you just bring this constant down, and then you multiply this by the derivative of the second factor, which is 2/3, L to the 2/3 minus 1. Okay, if you have trouble with that math, just write it out here for a minute. Okay, and so this is K to the 1/3 times 2/3 L to the 2/3 minus 3/3. I hope you can work with fractions. Okay, shouldn't be very difficult. So this is negative 1/3. Okay, well, I know we're working with fractions here, but shouldn't be difficult. I want to put a square around this, not to confuse it with a circle here. So you bring the circle down because it's a constant, and we differentiate what's inside the square here. So you bring the old exponent down front, and you bump the old exponent down by 1 to get the new exponent. So that's all we've done here. We're working with fractions, but that's okay. Now, it may be that you want to write this as 2/3 K to the 1/3 L to the negative 1/3 or something. There's a couple different ways to write this. You should know from your algebra course. You could also write this as 2K to the 1/3 over 3L to the 1/3. With the negative exponent, you can bring it across the fraction bar, change the sign. I hope this makes sense here. Let me see if I can back this off just a little bit so you can see the whole thing. But we acquired the derivative right here, really. And this is what I want you to be able to do. This is the marginal product of labor. Okay, so we're holding capital fixed. So this is a short run measure. So why is it short run? It's because we're assuming capital is fixed. You know, the short run is a length of time during which one of your inputs is going to be fixed. If you think about it, that's kind of a reasonable definition for the short run. It's not some arbitrary length of time like 6 months or 2 years or something like that. It just depends on the industry and so forth. But if it takes a long time to get a new machine, you can change labor on a day-to-day basis, but certainly not machinery. Then this might be an important measure for a manager. What's the marginal product of labor? So this is telling us, how does output change as we change labor, say by 1 unit? If we hire one more worker, how will that change our output? Okay, that would be the marginal product of labor. Okay, so I hope that makes sense. How about the marginal product of capital, NPK? This would be the derivative of Q with respect to K. So we come back up here. Let me back that off a bit so we can see it. Let's work with the same function right here. So now you're going to treat what's in the box here as a constant, okay? So if you want to write that first, you can. That's okay. So now you're going to differentiate this with respect to K. So this is 1/3 K to, well, what's the new exponent? That's 1/3 minus 1. 1/3 minus 1 should be minus 2/3, right? So this would be L to the 2/3 times 1/3 K to the minus 2/3, okay? So another way of writing this then, I guess, would be L to the 2/3, whoops, sorry, 2/3 over 3K to the 2/3. Remember, you can change the sign on your exponent here by bringing this across the fraction mark, bringing it downstairs in the fraction, okay? So, but at any rate, I hope this makes sense. The rest of it's just basic algebra, okay? Maybe it may have been a while since you've done that, but at any rate, that should make sense to you. Okay, so this is really what they're telling you here at the bottom of page 147 in your text. If you have a Cobb-Douglas production function, something of this form here, the marginal product of capital, which is the partial derivative of Q with respect to K, which is kind of what we found right here, is in formula form, it's this thing right here. It's A, K to the A minus 1, L to the B. Now that's what we've got right here, okay? This is, if I use the formula again here, this is your L to the B right here. So you're going to use that again, but let me let me just put it this way to make sure you understand how the formula makes sense. They say if you start out with a Cobb-Douglas function, uh, again, of this form here, KAL to the B, K to the A, which would be K to the 1/3, L to the 2/3. That's what we started out with way up here. So if we start out, then if you don't know the calculus, they're giving you a formula here to find the derivative. So if you don't understand the calculus, well, you got a formula here. Now, this is a plug and chug approach. To me, it's easier to understand the basic calculus, and you don't have to remember any formulas. But if you need help there, they tell you, okay, marginal product of capital. So a marginal product of capital, which is the derivative of capital with respect to of output with respect to capital. They tell you it's this AK A minus 1 L to B. See that here? That's what they're saying. And so, you know, this is then would be 1/3 K to the 1/3 minus 1, which is negative 2/3, L to the 2/3. Okay, which is again L to the 2/3 over 3K to the 2/3. That's what we got right here. All right. Likewise, you should be able to see how this formula, if you don't know the calculus, you could use this formula here to get the marginal product of labor, which is what we did here. But again, so you got to know these marginals, know how to find marginal product for you to be able to work any real world problems really in microeconomics. So I can't make much apology for that. Okay, that's just a very important tool to have at your disposal. Okay, I think what I want us to do next is work problem 1 here. Instead of giving you a printed solution for problem 1, I want to do this on the video. In part C of problem 1, we'll look at how you actually derive the demand for labor using the value of the marginal product. And so, so at any rate, let's go to problem 1. Okay, let's see how I want to do this. How about this way? Okay, so this is problem 1 in your text. It says a firm's analyst estimate that the firm can manufacture product according to the production function. Now, what kind of production functions? That's a Cobb-Douglas production function. Okay. We'll have more to say about why this is special later. But let me write it out here. Q equals K to the 3/4 L to the 1/4. And notice again the exponents add to 1 here, so forth. So they ask you some questions here. Calculate the average product of labor when the level of capital is fixed. So we're talking the short run here, 81 units, and the firm uses 16 units of labor. How does the average product of labor change when the firm uses 256 units of labor? So first off, I'd say, when K is 81, that's what they say to assume, and L is equal to 16, then we can find output. Output is given by the output function. So this is going to be 81 to the 3/4 power times 16 to the 1/4 power. Okay, or you can use if you want 81. Now there's a way to break that apart, but if you want to use 0.75 times 16 to the 0.25 power, that's okay. Now most calculators will have a y to the x key or exponent key, or this key here I have on my TI-34 calculator. So you should be able to get some facility at doing some of this. Like, for instance, if I want to get 81 to the 0.75 power, let's see if I can back this off a little bit. and maybe so we can see it. So you'd go 81, and then you hit the exponent key, okay, and 0.75, and hit enter here. You got 27. So this is equal to 27, okay? And then you got the 16 to the 0.25 power. So you could do all this in one step, but if you're unsure yourself, you want to break it down. So let's take this to the 0.25 power, and this is 2, okay? And 27 times 2 is 54. Okay, so that's the output. Okay, calculate the average product is what they want. So this is a step along the way. The average product of labor is Q divided by L. Remember that? So we'd have to take the 54 and divide it by 16. Take 54 divided by 16, you get 3.375. So this would be 3.375 units of output, whatever it is we're making, per what? Per worker, okay, or per labor hour, whatever the unit of labor is, okay, per unit of labor could be okay. Maybe it's a worker hour or it's a work day or what have you. I don't think they told us in this problem. Okay, so and then they tell you, how does this average product of labor change when the firm uses 256 units of labor? So you do the same thing, you just replace L with 256. You can check that out. I've got this, I'm going to save myself a little grief here and just say that we've got this calculated here for us right here. It's right here. You put 256 to the 0.25 power. You should get 108. If you need to pause the video and look at this line, you certainly can. And average product of labor then is 108 here divided by 256. It's 0.422. So this is the new average product of labor, and this was the old average product of labor. So you see that the average product of labor went down significantly. And might think about why in this particular case the average product of labor went down. But at any rate, that's part A of this problem. Part B, they say find an expression for the marginal product of labor when the amount of capital is fixed at 80 and so forth. And so again, you've got this output function, K to the 3/4, L to the 1/4. And here in part B, number 1, and they want you to find the marginal product of labor. So the marginal product of labor, what is that? Remember, that's the derivative of Q with respect to L. Or, pardon me, to be real technical here, precise, it's the partial derivative of Q with respect to L. So you're going to treat K as a constant here. So this just kind of comes down. This is K to the 3/4. And you multiply this by 1/4, L to the 1/4 minus 1. Okay. So what would this be? This is K to the 3/4. Okay, 3/4 divided by 4. This would be L to the negative 3/4 here. Or if we put it downstairs, it's to the positive 3/4. That might be an easy way to write that. Okay. You can write it this way, or you can write, there's a variety of ways you can write this. But you could write it as 1/4 K to the 3/4, okay, L to the negative 3/4. But a lot of times we like to write our final answer with positive exponents. Doesn't matter, that you can work with either form and do the calculations that they want you to do. So at any rate, when the amount of capital is fixed at 81, they want you to find the marginal product of labor and illustrate that it depends on the amount of labor hired by calculating the marginal product for 16 and for 81 units of labor. So first off, they say, let capital here again be 81 machines, 81 units. And then in this case, find the marginal product of labor under 2 different scenarios, if you will. Okay, what's the marginal product of labor when L is equal to 16 units and L is equal to 81 units of labor? So that's, you see, that's what they're asking you to do here. Capital's fixed at 81, so you can't change the number of machines. It's 81 units capital. But what if you varied your worker level from 16 to 81? How would that affect your marginal product of labor? Okay, so that's really the question here, is to find the marginal product at these two different levels. Well, so you're going to use this formula here and evaluate it at these two different combinations for K and L. So over here, the marginal product of labor is, 1/4 or 0.25. K, which is 81 to the 3/4. L, which is 16 to the negative 3/4. Now, if you just want to use your calculator, you can write 0.25, okay? 81 to the 0.75 and 16 to the negative 0.75. So you can go through this same thing if you want, using your calculator. Let's find out what this is here real quick. Clear. Okay, so I'm going to do these separately here. So like the 81 to the 0.75. So that's 27. So this is 27. So I've got 0.25 times 27. And then I'm going to multiply this by 16 to the negative 0.75. Hope that makes sense. So this is 0.125. So I'm going to take 0.125, multiply by 27, and then multiply by 0.25. And I get 0.84, it rounds to 8.44. Okay, you see that? Okay. And then I'm going to come over here. I'm going to do the same thing. Okay. But what's my marginal product of labor now? It's going to be different than it was over here. Marginal product of labor now is going to be 1/4. Is using this formula again here. It's 1/4 times units of capital to the 3/4. So this is 81 to the 3/4, just like we had before. But now this is, instead of 16 like we had over here, it's 81 to the negative 3/4. Okay, 81 to the negative 3/4. And so, I don't know, you might be able to do this one in your head. Okay, this is kind of a special one. This is 0.25, 81 to the 0.75, divided by 81 to the 0.75. Remember, you can change the sign on your exponent by moving across the fraction bar. And guess what? These just cancel. So this is 0.25. All right. So the marginal product of labor went down, right? Marginal product of labor went down as we increased the amount of labor we're using. Very important, very, very important relationship here. Your book talks about this, and read through this, but notice that for a fixed level of capital, so we're in the short run. So say if capital is fixed, so for a fixed level of capital, just put a bar over it or a star, it means it's fixed. Then the marginal product of labor decreases. It decreases as the level of labor increases. Notice we went from 16 units of labor to 81 units of labor. Okay, that's what happened here, right? We're using more workers. Marginal product of a worker goes down. Your book spends quite a bit of time talking about, and I do this too on the review videos. The concept is here in that review of the principles of microeconomic theory. In the short run, the marginal product of a unit of well, of one of your inputs, okay, whether it's labor or capital. But marginal product of labor is going to decrease as you use more labor. Okay, you get less bang for worker as you hire more workers. Okay, so I talk about in the video about a plant. I think I draw a plant there where there's, I think it's, if you go back and look at the videos, there's the little plant that has 4 workstations where they make baseball bats. I talk about how that thing is really humming along at 4 workers. You can assign 1 worker per station. Now you can push output up higher for the same plant size. So this is a short run decision by hiring a 5th worker and a 6th worker. But at some point, you start to get overcrowding. Okay, the marginal product goes down. And this is something eventually, this always happens in the short run. The marginal product of a variable input decreases as you hire more and more units of that input, whether it's labor or capital. Okay, so make sure you understand that and you follow that. And that leads to something they give you in your book. Okay, this leads you to this what's called the profit maximizing input usage rule. And in my edition of the book, this is on page 143. So if we look here just a second, I want you to see this. First off, this table they develop. We'll come back to this rule here in a minute, but above here, they develop this table for a short run situation. You'll notice here that the marginal product of labor, the variable input, they don't have a fixed input here, which is capital, and there's no reason to, it never changes. But notice as we add more and more workers here, the marginal product goes up for a while, but then it always eventually goes back down. That's the short run rule here, if you will. That's a short run law here. Marginal product of a variable input will always drop off because you have this overcrowding effect. So you initially have, and I talk in the review videos a little bit about why this might go up. Initially, it's because of specialization, but it always goes down. But you're going to use this in conjunction with the output price to tell you how much labor to hire. You want to continue to hire workers so that at some point here, the value of the marginal product drops to the wage rate you're paying your workers, basically. So the value of the marginal product is computed over here with these 2 columns. This is the marginal product. This is telling you what an additional worker will do for you. It's a change in output divided by change in labor. So like when we hire the 7th worker, output, that's going to affect output by 292 units. That is to say, 7 workers can produce more than 6, okay? The 7th worker is going to add 292 units to your total output. The ratio of delta Q to delta L here is the marginal product here, and that tells you how total output is affected by change of 1 worker. 1 worker is going to add 292 units, say tables or chairs, use chairs, 292 chairs in a week. Multiply by the price per chair, and that gives you the value of the marginal product. So this is telling you kind of how your revenue is going to be affected by hiring additional workers over here. You take the additional output and multiply by the price of your output. We're assuming a competitive output market here. We could loosen that later, but at any rate, this is the value of the marginal product. And so you're going to keep hiring workers until the value of the marginal product falls to the wage rate. Okay. Now, your book talks how initially you want to get beyond a bump here. You want to get to the part where it starts to come down and it approaches the wage rate. So for instance, you want to hire 9 workers here. That 9th worker is going to increase the top line on your income statement, if you will, the revenue, by $516. It only costs you $400 to get that 9th worker. So the value of the 9th worker, the marginal value or the value of the marginal product is $516. They're only going to cost you $400. So that's a good worker to hire, but you wouldn't want to hire the 10th worker. the 10th worker is going to cost you more than they're going to deliver. Okay. So your book has a discussion. Well, that's the point behind this table. Okay. And I think it's problem 2. You got to build a table like this and so forth. And this is where you get into building what's called a labor demand function here. I think that there's probably one of these in your book. Yeah, here we go. This is called labor demand function. The downward sloping part of the value of the marginal product curve is called labor demand curve. Why is it called the, whoops, why is it called the labor demand function? Like any demand function here, it's giving you price of a commodity, but this is the price of a resource. And think back in when you first learned what a demand curve is, you had the price axis is vertical and quantity axis is horizontal. Same thing here, but this is the price of a resource and the quantity of the resource demanded. It's not a product or an output, but it's a resource that we're looking at the demand for. And so they plot this value of the marginal product curve. So notice it goes up and then it goes down. And what they're doing here is, this is on the previous page, is they're plotting this curve here. It goes up and then it goes back down. Okay. So that's why this curve here goes up and goes back down for differing levels of labor. At any rate, you want to get past the first few workers so that you're coming back down, and you continue to hire workers until the value of the marginal product falls to the wage level. Okay. So this section of the value of the marginal product curve gives you a relationship between the price of labor and the quantity of labor you want to consume. If the price of labor, which is called the wage, goes down, guess what? You want to hire more workers. Hope that makes sense. If workers become cheaper, you want to hire more workers. If the wage rate goes up, you hire fewer workers. This is shrink this way. Okay. So this is how you get the demand for labor curve. It's the downward sloping portion of the value of the marginal revenue, of marginal product curve. So that's what they're saying right here. Okay. To maximize profits, a manager should use inputs like labor at levels at which the marginal benefit equals the marginal cost. More specifically, so in this situation, when the cost of each additional unit of labor is W, the manager should continue to employ labor up to the point where the value of the marginal product equals W in the range of diminishing marginal product. That is to say, you don't stop here at hiring this amount of workers when you're going up in the value of the marginal product. Okay, you want to get past, and that's the point in this table here. You don't want to stop with the first worker, because the second worker, the first worker, I guess you wouldn't hire the first worker because they would cost more and then they would deliver. You want to get past that. You want to get on down here ways where you're descending on the value of the marginal product curve to the wage rate. Okay, so this is the demand for labor curve. Okay, so that's going to bring us to part C of problem number 1. Okay, part C of problem number 1. So let's look at that, because they're going to want us to find out how much labor we should hire. Okay, that's how you would derive a demand for labor curve. You look at the value of the marginal product. Let's see. Okay, so again here, suppose capital is fixed at 81 units. If the firm can sell its output at a price of $200 per unit of output, and it can hire labor at $50 per unit of labor, how many units of labor should the firm hire in order to maximize profits? So what we have to do is we have to equate the marginal product of labor to the wage rate and solve for L, basically. In other words, set the value of the marginal product equal to the wage rate. So what is the value of the marginal product here? The value of the marginal product of labor. Okay, so let's compute this. Okay, so this is going to be the price of our output. That's going to give you the value of your workers. I mean, that's why you hire workers, right? You just think logically on this. You hire workers so they produce output, so make chairs or whatever. So what's the value of the marginal product of labor? It's the price of the output times the marginal product of labor. So they're telling you what the price of output is. It's $200 a table, okay? $200. And the marginal product of labor, okay? Well, we got to go back and find the marginal product of labor using our marginal product formula we just did. And what's a marginal product of labor when the capital's fixed at 81 units? How much labor would you want to hire? Okay, that's, or what would be the marginal product of labor? Okay, so I had to find out where, go back and look at this. What was our marginal product of labor in part B? Okay, we just did this. It's this formula right here, and they say use 81 for K again. So I'm going to insert this right here for marginal product of labor. Okay, so the marginal product of labor here again is 1/4 K, which is 81 to the 3/4 times L to the -3/4. Okay, so we're wanting to find out how much labor to hire. Okay, there we go. And when capital's fixed at 81. So I'm using this formula that we derived a while ago for marginal product of labor. I'm putting that here for marginal product of labor. Okay, so we need to simplify this expression here. So I guess you could say that this is 200 times 1/4 is, 0.25 if you want. You can do this on your calculator, 81 to the 3/4. Now I can do this one in my head. Maybe you can too from algebra. It's 81 to the 1/4, which is 3, and 3 cubed is 27. But if you need to use that key on your calculator, that caret key, do so. It's no big deal. And then L to the -3/4. Okay, that's the value of the marginal product. So let's combine these constants here, kind of get those out of the way. I think if you multiply 200 times 0.25 times 27, I think you get 1350. So this is 1350 L to the -3/4. Now you set this equal to the wage. What are they telling the wages? How many workers do you want to hire when the wage is $50 a worker? So you set this equal to 50. Okay, set that equal to 50. So the value of the marginal product, which is the price, okay, price of your unit of output times the marginal product of labor, which we did in part B. Multiply this out for K is 81 machines, or units of capital. Tells you how many workers to hire once you set it equal to the wage rate. Okay, this is the wage. You set it equal to the wage, W. Okay, value of the margin product, you set equal to W wage. Okay, so that's kind of a little formula they give you in your book for finding the demand for labor. So at any rate, we solve for L here. Okay, so solve for L in this formula right here. So, a couple different ways of doing this. 1350 divided by 50. Okay, I'm going to divide both sides by 50 times L to the -3/4 is equal to 1. And I'm going to just multiply by L to the 3/4. L to the 3/4, 0.75 is equal to 1350 over 50. Okay, so I need to find out what L is, right? So maybe you recall back from school that you can get the first power here by multiplying by the 4/3 power. 3/4 times 4/3 would be to the first power. So I'm going to take 1350 over 50 and multiply this. I want to take both sides to the 4/3 power. Okay, 4/3 power. So L is equal to 1350 over 50 to the 4/3 power. Let's see what that is real quick. Okay, let's see, 1350 divided by 50 is 27. So 27 to the 4/3 power. So, I mean, we can do that on our handy dandy calculator easily enough. Let's see here. So 27, shoot. Okay, hang on, class. You back this off where you can see it. So 27 raised to the 4/3. So I'm going to need to use my parentheses here. 4 divided by 3. No big deal. You get 81. L equals 81. So what's the significance of that? You want to hire 81 workers or 81 units of labor if you have 81 units capital. Just so happen to work out that way in this problem here. If you're paying your workers $50 an hour or $50 per unit of labor. Now, if the wage goes up, then it should make sense that L is going to go down. Okay. So if the wage goes up here, L is going to go down. So if this is at 100, then you're going to get a smaller value for L that would solve this equation here. Okay, so I hope that makes sense and how we got down here to the labor demand. In each case, I'll just say before I go off camera here, that if you want to find the labor demand, again, you take the value of the marginal product. The value of the marginal product of labor is the price times the marginal product of labor, price of the output. You set it equal to the wage rate. Okay. And same thing for capital. Okay. But you set the value of an additional worker, that's the value of the marginal product, equal to the wage you got to pay them to determine how many workers that you got to hire. Okay, so I hope this is helpful. Kind of problem number 2 you're going to do in conjunction with this is just kind of a straightforward calculation where you build that table. I will say one other thing here, okay? Pardon me, excuse me, really fighting this cold. One other thing that you'll need to use. Okay, this in my book is on page 153. This is called, I don't know what it is in your book because there's different releases of this book, so I'll try to avoid page number specificity when I can, but let's go to the camera here. This is called the cost minimization input rule. This rule here tells you how many units of labor and capital you should use to minimize the cost of producing any level of output. Okay, now think about that. That's a very real world problem. So you could hire a bunch of machines and a few workers, or a few machines and a bunch of workers. A lot of times you have a choice. You can substitute between workers and machinery. Sometimes it turns out to be in a fixed rate. Your book shows that a little bit with a problem or two, but generally speaking, that kind of varies over output or over input levels. But I'm just saying that you have different combinations, if you will, of workers and machines that you have to choose from to produce any level of output. So I hope it sounds like a real world problem to you. To know that you need to be able to select which of those combinations would you want to use to produce output at minimum cost. Which one of those combinations that could produce, say, 100 units, 100 tractors in a month, which combination of labor and capital would you select? It would be the combination of labor and capital that comes at the lowest cost. And so that's what this rule here tells you. You want to select units of labor and capital. So to minimize cost of production. Okay, I'm just going to write it out here. Select K and L that would satisfy this thing right here. That would say that the marginal product of labor over the price of labor, which is the wage rate, equals the marginal product of capital over the rate at which you hire capital. That's called the rental rate of capital. You may have to rent your machines or whatever. Okay, if you buy them, you still depreciate it over time. You look at it as a rental rate. But let's think about it as renting machines and renting people. The prices at which you do those things are the rental rate of capital and the wage rate. This is what you'd satisfy. Now you'll have a problem, I forget which problem, just problem or two, where you realize to minimize the cost of production, you want to select the values of K and L that would satisfy this relationship. This is kind of like getting the same bang per buck over each of your resources, labor and capital. This is like bang and this is like buck. Okay, you got the same thing with respect to product markets as well, but we're looking at resource markets here. We're looking at hiring labor and capital. So I don't have the problem in front of me for at the moment. I guess I could grab that here and we could look at it together. But if, for instance, if you had a situation where the marginal product of labor over the wage rate were greater than the marginal product of capital over the capital rental rate, if this were the case, then you need to be able to logically figure out what you would do as a manager. If this is the case, then what you need to do is to get this equality here is you need to drive this fraction down and this fraction up. Now, typically, managers have no control over the wage rate or the rate at which they rent capital. Okay, they compete with other businesses for workers, so they have to pay a certain wage, and they, rent the capital from equipment supply store, what have you. So these two things, in this chapter anyway, we're going to assume are kind of given to the manager. They have to accept these things. So it's these things here that you have some control over. So let me ask you here, given some basic economic theory that we've introduced so far, if this were the case, what would you do? Okay, would you hire more laborers and fewer work and less capital, or would you hire more capital and fewer workers? Well, you got to drive this down. You have no effect over the denominator, so you need to drive this denominator down and this, I'm sorry, numerator down and this numerator up. And the only way you can drive this numerator down is by hiring more workers. Okay, hire more laborers. Why? Because there's this thing again called the diminishing marginal product of labor. Okay, again, in the short run, as you hire more and more workers, the marginal product of workers goes down. Remember us looking at that in that table just a moment ago? So we'll hire more workers, so this would cause, I'm going to say causing marginal product of labor to go down. You hire less capital, thus causing the marginal product of capital to go up. And so the result here is you basically, in the next period of time, you hire fewer workers, or maybe today you fire some workers. I'm sorry, you hire more workers. I'm sorry. So you hire more workers and you get rid of machines. You replace machines with workers, if this is the case. If this inequality were reversed, then you would do the opposite thing. But you're going to use the fact that marginal product of a variable input decreases as you hire more and more units of that variable input. So hire more labor, cause this to go down, but as you hire more labor, you can hire less capital, and you're going to cause this to go up. Okay, I hope this was helpful tonight, class. I keep hitting the pause button because I'm fighting this cold and I cough. And then where was it? Papers go to the wind, what have you. But we covered some very important concepts there. If you need to watch this video again, please do. I really believe we covered here in this video anything that might be missing in the theory for you, or for those of you who've not had a course in calculus, or it's been a while since you've had even a principles level micro theory course where we talk about things like diminishing marginal product and so forth. Now, I'm teaching an undergraduate principles course right now, and we're about to cover some of this same material. We're not quite there yet, but we're about to talk about the demand for labor before the semester's over. And here we are on November the 9th as I make this video. So we got 3 or 4 weeks left in the semester. So we'll be covering this topic in there as well. And I may be posting those videos up for you as well. But some of these other things about production and so forth in the short run, where you have the S-shaped output curve and all of that, that they talk about in this chapter. I have provided some review for you in the way of those principles level videos. So you might want to go back and view those. Let me know if you got any questions, okay? I'll be happy. I'm here to help you. So reach out to me and let me know how it's going. So hope you have a good evening, and I'll hope to talk to you again soon. Bye bye.